This is the 15th lecture and we continue our discussion on single tuned circuits. To review briefly what we had done earlier, we had taken a voltage source in series with a resistance, an inductance and a capacitance, and we chose to take our output voltage across the capacitance. Sure. It won't be the same response now. Response would be slightly different. But our transfer function, which is h of s V0 by Vi, we wrote it in the form 1 over LC divided by s squared plus R by Ls plus 1 over LC, and we put this in the form in terms of its poles and zeros as s plus alpha whole squared plus beta squared and alpha squared plus beta squared. We also put in a slightly different form in terms of omega n and zeta, and we showed that this is omega n squared divided by s squared plus twice zeta omega n s plus omega n squared, where zeta is defined as the cosine of the angle theta. This is minus alpha and this is plus j beta. Theta is defined as the cosine of this, zeta is defined as the cosine of this angle theta. These are the three different forms for representation of the same transfer function. And in terms of alpha and beta, if I write this again, j omega sigma and the poles are, let's say, at beta minus beta, this is minus alpha and this is j beta, then it showed that the response, that is h of j omega magnitude, has peaking if beta, this peaks if beta is greater than alpha, that is theta is greater than 45 or zeta, which is equivalent to zeta less than 1 by root 2. Agreed? And we showed this by means of a peaking circle. That is, what we did was we drew a circle with this point as center and beta as radius, then this circle cuts the j omega axis at j omega m, and this is the frequency at which the peaking occurs. We also showed that omega m squared is equal to omega n squared multiplied by 1 minus 2 zeta. All right. This is the frequency at which the peaking occurs. This also shows that if zeta is greater than 1 by root 2, I made a mistake here. Zeta squared, yes. If zeta is greater than 1 by root 2, then this quantity is negative and therefore there is no maximum. Zeta equal to 1 by root 2 is a critical condition under which the maximum occurs at 0 frequency. Now these observations will now be useful in finding out the so called half power points. Half power points. If zeta is greater than or equal to 1 by root 2, that is theta is less than 45, then there is no peaking and the response the magnitude response versus omega, h of j omega magnitude, would be something like this. What is the DC response? The response is 0 frequency. It is, well, you remember the transfer function s squared plus twice zeta omega ns plus omega n squared. So at s equal to 0 it is equal to 1, isn't it right? So it starts from 1, it starts from 1, and then if the damping is greater, damping coefficient is greater than or equal to 1 by root 2, no peaking occurs, and therefore it must be a low pass response like this. Whether zeta equals to 1 by root 2 or greater than 1 by root 2, it shall always be like this, and therefore all that one can define here is a frequency omega sub c at which the response is 1 by root 2 or 70.7% down, and as you know, omega c is called the bandwidth of this low pass filter. It becomes a low pass filter, and this case is hardly of any interest, but nevertheless it is of interest to find out what omega c is. Omega c is defined as the 3 dB cutoff, 3 decibels cutoff, that is the frequency at which the response is 70.7% of the maximum response, and the maximum occurs at DC. All right. On the other hand, if zeta is greater than, if zeta is less than 1 by root 2, that is theta is greater than 45, there shall be a peaking and suppose the peaking is like this, where the maximum is less than 1 by root 2, this is less than root 2. All right, the maximum occurs at omega m, this is omega, but the maximum value is less than root 2. All right, then obviously 70.7% down from this value shall occur only at one frequency. All right, if this is less than 1 by root 2, then 1 by root 2 times this will be somewhere here, okay, max, let us call it max, max less than 1 by root 2, and this is max by root 2 shall occur only at one frequency, and this is omega c. So there is still one cutoff frequency, only one cutoff frequency, because the DC value is greater than max by root 2. All right. One might argue, if I extend on the negative frequencies, will it come down? No, the magnitude response is even, and therefore the magnitude response will be like this, it does not come down. Okay, it is even function, magnitude h of j omega. It is the same for omega positive and omega negative. All right. Now suppose theta is less than 1 by root 2, that is zeta is less than 1 by root 2, and theta is greater than 45, in such a manner that the max is greater than root 2, then my magnitude function shall vary like this. You start from 1, go through max at omega equal to omega m, and since maximum is greater than root 2, 1 by root 2 of the maximum shall now occur at two frequencies. Let us call them omega c1 and omega c2. These are the frequencies at which the magnitude response is 3 decibels down from the maximum value. The maximum is taken as 0 dB, then these will correspond to minus 3 dB. Or in terms of power, if this voltage appears across a 1 ohm resistor, then in terms of power, the power shall be half at these two frequencies as compared to the power at the maximum frequency. So these are also called half power points, as you know. And it is of interest to find out what these half power points are. All right, And one of the ways that this can be done is through geometrical construction.
Excuse me, sir.
Yes.
So this graph starts at 1.
It always starts at 1 because the transfer function is omega n squared divided by s squared plus twice zeta omega ns plus omega n squared. And therefore, at s equal to 0, that is dc, the value is 1, omega n squared by omega n squared. It should also be obvious from the circuit. If you draw the circuit, we have a resistance, an inductance and a capacitance. This is the input, this is the output. So if it is DC, the capacitor acts as open, the inductor acts as short, and therefore all the voltage appears here. So it always starts at 1. Alright? It would not be so had we taken the voltage across the inductor. It would have started from origin at 0. Is that clear? If we had taken the voltage across the resistor, then also it would have started from 0. It is because we are taking across the capacitor, this peculiar situation arises. Alright? And if the voltage is taken from the inductor or the resistor, there shall occur, whenever there is a peak, there shall occur 2 cutoff frequencies. Alright? But here, 2 cutoff frequencies arise only when the maximum is greater than root 2, not otherwise. If the maximum is less than root 2, then only 1 cutoff. Okay? It is of interest to find out where these cutoff frequencies occur. And this can be done by a graphical construction like this. So our aim now is to find the values of omega c 1 and 2. There are 2. If there are 2 cutoff frequencies, we want to find both of them. All right. For this, we consider this pole 0 diagram again, and let's say these are the poles. Somewhere here, okay. These are the poles, and this is minus alpha, and this is j beta. Let's consider an arbitrary frequency of j omega, let's say. We want to find out the magnitude at this frequency. That is, we want to find out h of j omega magnitude. Then, by the graphical construction, what we do is we construct a vector from the pole to j omega and a vector from this pole to j omega. Let's call this as m1 and m2. For reasons to be made clear, let's extend m1. Let's extend m1, okay? Let me use a different color. And let us call this angle as psi. Okay? The angle between the 2 vectors as psi. Just the magnitude. We don't care about the sign at the moment. Okay. Then the area of this triangle, the shaded triangle, obviously is half, base is 2 beta, and the height is alpha, and therefore the area of the triangle is simply alpha beta. Is that clear? This is a product of the real part and the imaginary part. This is 2 beta, the height is alpha, so half 2 beta multiplied by alpha. It can also be found out in terms of m1 and m2 and the angle psi. Now look at this construction. What we do is we drop a perpendicular on this. We draw a perpendicular on the extension to m1. Okay, this is the perpendicular. Then the area of this triangle is half m1, the base, multiplied by height. Height can be found out in terms of m2. This angle is 90, 180 minus psi. Okay, pi minus psi. And therefore the height would be m2 sine of pi minus psi, which is precisely sine psi. So this would be half m1 m2.
Sir, which triangle we are finding? The area of which triangle?
Area of the shaded triangle, the same triangle. Same triangle, I am first finding out in terms of alpha and beta, next in terms of m1 and m2. and I am considering half of the m1 as the base and this as the height. This height is found in terms of m2 and this angle is pi minus psi. Therefore, the height is m2 sine of pi minus psi, which is exactly equal to sine psi. Alright. So, therefore, the reason for finding this out is that m1 m2 therefore is equal to 2 alpha beta divided by sine psi. Alright. m1 m2 equal to 2 alpha beta divided by sine psi. You also know that the magnitude at any point at any frequency is given by omega n squared in the numerator, and in the denominator you shall have the magnitudes of the two vectors drawn from the poles to the frequency, that is m1 m2. Alright. The magnitude at any frequency is given by, is this clear? What was our function? Omega n squared divided by s minus p1 star. If you call this p1 and this as p1 star, then the magnitude at any frequency is simply the product of the zero factors divided by the product of the pole vectors. There are no zeros, and therefore it is only the product of the pole vectors j omega minus p1, j omega minus p1 star. And since m1 m2 we have found out, we see that this is equal to omega n squared divided by 2 alpha beta multiplied by sine psi. And you call this k sine psi. This is a constant. As frequency varies, as omega varies, k remains a constant, it is only psi which varies. Okay. So, if with the variation of omega I can find out the values of psi, then I know the variation of magnitude with frequency. But interesting thing is that instead of two pole vectors, both of which are functions of frequency m1 and m2, if I increase omega, m1 will increase, m2 will decrease, and so on. Instead of two pole vectors, I have reduced the magnitude variation investigation to that of investigation of just one variable, that is the angle psi. Okay. Which is a very interesting phenomenon, because you notice that the max will occur when psi is equal to pi by 2, right, because the maximum value of sine psi is 1, which occurs at psi equal to pi by 2, and the maximum value is equal to k. Maximum value equal to k when psi is equal to pi by 2, and we know where that occurs. We have to draw a picking circle with this as the center and this as the radius. We draw a picking circle, wherever it cuts the j omega axis is the frequency omega m. At omega m, the angle subtended between m1 and m2 must be equal to pi by 2. Alright. We can also do this analytically, but we shall lose sight of the physical picture as to what is happening, and geometry is much more beautiful than pages of algebra. I find this very intriguing and interesting. Okay. So, all that we have to find out now is the values of omega at which the angle psi becomes equal to pi by 4. If we want to find out the half power frequencies, all that we have to find out is the frequencies omega c1 and omega c2 at which psi is equal to pi by 4. Agreed? At these frequencies, sine psi will be 1 by root 2. So, the magnitude would be precisely k, the maximum value, divided by root 2. Okay. Maximum value k is 1, that you know, but I have put it for generality's sake. Okay. So, the the problem is therefore to find out omega c 1 2, and for that all you need to is to make a geometrical construction to locate the point or points at which psi is equal to pi by 4, and this can be done by means of a very elegant diagram which I will show now. I will explain this carefully so that you can follow this. You see, this is the sigma axis, this is the j omega axis, okay, and these are the two poles, one is here and the other is here. This point we call as A, and this point we call as, no, I beg your pardon, this point we call as, A is already marked, so let us call it as C. Or is C is also marked? No, it is not marked. Okay. So, these are the two poles, B and C are the two poles. Then the distance from the origin is alpha, this point is minus alpha, and B has the y coordinate or j omega coordinate as j beta, alright. This is minus j beta, alright. Then to draw the peaking circle, what we do is we take this point as the center and beta as the radius and draw the peaking circle. The green circle is the peaking circle, and naturally this is equal to j omega m, the frequency of the maximum, alright. And you know that if beta is less than alpha, then there will be no peaking circle, there will be no peaking. If beta is equal to alpha, then the peaking circle, that is the point A, shall be at the origin and the j omega axis shall be tangent and all that we know. Now what we do is the following. If I draw the peaking circle and I join, and this peaking circle intersects the sigma axis at the point A, I join AC and AB, then the angle subtended would be the angle subtended by a diameter on the circumference, and therefore this will be 90. Is this point clear? This angle would be 90. What we do now is to take A as the center and AB as the radius, AB or AC, which is the same, the distance will be the same, and draw this red circle, not red, the orange circle. Okay. Let the orange circle intersect the j omega axis at j omega c. As you can see from the subscript, this is the half power point. The reason is that this chord, the chord BC, subtends an angle psi 1 on the circumference and an angle pi by 2 at the center, and therefore psi 1 must be equal to pi by 4. Is this clear? A very elegant construction, very elegant construction. I repeat,
It is not the same for circumference.
it is not the same as, oh yes, this is the center of this orange circle. The chord AB belongs to both the peaking circle. For the peaking circle it is the diameter, whereas it is less than the diameter for the orange circle, okay. And A is the center of the orange circle, so the angle subtended at the center is pi by 2. The angle subtended on the circumference must be pi by 4, half of that, and therefore j omega c, that gives you the half power point. Unfortunately, it is only one. The other half power point cannot be obtained, at least you do not know how to obtain it geometrically. If you can obtain it, that would be a wonderful thing. I will ask Professor Kuo to put it in his textbook with your name mentioned there, if you can find out. Okay. Unfortunately, this omega c, is it the lower half power point or the upper half power point? Upper one, obviously, because it is greater than omega m. It is on the right side, and therefore omega c gives you omega c 2. All right. The the question now is how to find the lower half power point. Okay, omega c 1. Omega c 1, as we know, may or may not exist. Omega c 1 will not exist if the maximum is less than how much? Now root 2, if the DC value is 1, if the maximum is less than root 2, then omega C1 does not exist, and that is one of the reasons why a geometrical construction like this does not disclose omega C1, it only discloses omega C2. Okay? It is a fuzzy logic, it is not very clear as to why we cannot find out, and that is why I throw you a challenge.
So what you said?
Omega C1 may or may not exist, alright, may or may not exist. If it exists, then it can be shown, and that is not too difficult, I also leave that as a challenge. If it exists, if omega C1 exists, then one can show that omega C1 is equal to omega m squared divided by omega C2, which is obviously lower than omega m. Agreed? That is omega C1 omega C2, the product is equal to omega m squared. If one is greater than omega m, obviously the other must be less than omega m. Okay? Now let me put this as a problem to you. Show. Okay. This relationship, that is the product equal to omega m squared, is described in mathematical terms, in geometrical terms, as in terms of a symmetry. You see, if I have let us say x1 plus x2 divided by 2 equals to sum x3, then I say x3 is the arithmetic mean of x1 and x2. On the other hand, if I have omega m as square root of omega c1 omega c2, then I say omega m is the geometric mean. Okay? So omega m, the maximum, is geometrically symmetrical, the frequency of maximum is geometrically symmetrical about the two half power points. In fact, it can be shown that the complete response is also geometrically symmetrical. In other words, what it means is the following. We start from 1. On the other side, well, it does not have the same kind of symmetry as this. Same kind of symmetry would have meant that the curve falls like this. Okay? This is arithmetic symmetry. Arithmetic symmetry. On the other hand, the geometric symmetry will imply that the curve falls like this. Okay? It does not fall at the same rate at equal frequencies deviations from the maximum. Okay? Let me make a prophetic statement at this stage, which also you can prove, that near omega m, okay, one thing is that the response here does not show arithmetic symmetry, it shows geometric symmetry. This is also can be shown mathematically. Second thing that I make is that the statement that I make is that if the Q is high, what does this mean? Your definition is Q, figure of merit, is 1 by 2 zeta. That means if zeta is small, what does zeta small mean? That the peaking is sharper and sharper. Okay? That is, you have a high Q case, in other words, you have a sharp peak. If this is so, if the Q is high, then one can show that around omega m, that is for frequencies very close to omega m, the curve shows arithmetic symmetry. Okay? Response is arithmetically symmetrical. This requires some pages of algebra, and it is most convenient for me to leave that to you. Okay? So, I have made several statements and I have asked you to investigate. One is there a possibility to find omega C1 geometrically? Can it be done? And I promise that if you find a way, I will get it included in the next edition of Kuo's book. Okay? That responsibility I take. Number 2, I ask you to show that the product of omega C1 and omega C2 is omega m squared. Then the third point that I ask you to show is that in general the frequency response curve is geometrically symmetrical for a situation like this. And the fourth thing that I have shown is, I have told you that if it is a high Q situation, then around omega n response is arithmetically symmetrical. Okay? And I can assure you none of them will be trivial problems. None of them will be trivial problems. Okay. I did want to at one point of time I thought I might do it in the class, but I decided finally that it's more convenient for me to leave it to you. Okay. Let's look at the phase response. We have only looked at the magnitude response so far. Now the phase response, if I recall, the the frequency, the transfer function h of j omega is j omega minus p1 j omega minus p1 prime, p1 star. Okay, this is the frequency response for s equal to j omega. Now let me look at the phase response a bit systematically. I can of course substitute p1 and p1 star and do it analytically. I can find an expression for the frequency, for the phase response. But if you go from mathematics, from the mathematical expression, the chances of making a mistake is much greater in the case of phase response than in magnitude response, because the phase response there are ambiguities. 0 and 2 pi cannot be distinguished from the tangent of the function. Okay, tangent is the same. Tangent, why tangent? All trigonometric functions are the same at 0, theta equal to 0, theta equal to 2 pi. A change by plus pi cannot be distinguished from a change through minus pi, all right, and therefore a picture in the case of phase response is worth more than 1000 words, not just 1000. Okay, let's take the the plot. This is P1 and this is P1 star in terms of alpha and beta, all we have done so far. Now if I want to find out the phase at 0 frequency, 0 frequency is here. So draw the two vectors. Let me use a different color. Draw the two vectors. No, this is not what I wanted to use. Okay. Draw the two vectors and find their angles. Let this angle be called theta 0, then obviously this angle is minus theta 0, all right, and the sum of the two angles is equal to 0, and therefore phi j 0 would be equal to 0. Agreed? Is it okay? Minus 0 is the same thing as, you see, actually these are angles of the denominator factors. So when they go to the numerator, to make up the phase of h of j omega, you have to take with a negative sign. Okay, minus 0 is the same as 0.
So
yeah.
Here we are considering always the phase to be in the range minus pi to pi or 0 to 2 pi.
No, I don't understand this question.
So if it was on the other side,
You could take it to be 2 pi. Is that what you mean? This angle?
so but there should be a way, convenient rule that we will take it from minus pi to pi or 0 to 2 pi. So because
Oh, whatever the rule is, there is no ambiguity here. Whatever the rule is, we'll clarify the rule when we come to a particular situation. Okay, but here you see, one of the possibilities was take this angle, then the sum of the two angles is 2 pi, and therefore the angle would be minus 2 pi. Agreed? Now we are not going beyond 2 pi in any case, not beyond 2 pi, okay, between 0 and 2 pi. It could be minus pi to plus pi or 0 to 2 pi, it does not matter. If minus pi comes, we have no other way, we cannot convert it to any other phase. Okay. So this phase is 0 or minus 2 pi as the case may be. If you want to extend beyond 2 pi, you are most welcome, it does not make a difference. Okay. Now if I take a frequency slightly away from origin, let us say here, then what happens to this angle? This angle increases. Okay, this becomes, let us say, theta 0 plus delta 1. On the other hand, this angle decreases. Let us say this angle becomes theta 0 minus delta 2. Agreed? And the sum of them, that is, as omega is greater than 0, the sum of them, the phase now becomes delta 1 plus delta 2. Agreed? The sum of them, but with a negative sign, minus delta 1 plus delta 2. All right. When it is here, when omega is close to j beta, when omega is close to beta, then this angle becomes 0 and this angle becomes close to pi by 2, not quite pi by 2.
That is delta 1 minus delta 2.
It will be depending on alpha and beta.
This is delta 1 minus till, no, there is a minus here. So minus and minus makes plus. This plus this. Yeah, so what did you say?
Sir, you are saying that it will become close to pi by 2.
Huh.
So it will be depending upon alpha and beta.
Correct. So what I am saying is, if beta is much larger than alpha, a high Q situation, it will be close to pi by 2. Not quite pi by 2, it will be less than pi by 2. Minus pi by 2, not plus. Okay, the angle is still negative. Why? Because these angles are in the denominator, you have to take it to the numerator, so the sign is negative. What happens? The next point that I have to consider is, but at the same time you notice that as soon as we cross the peaking, that is omega m, well, we will come to that later. Now the other frequency that you have to consider is infinity. As omega goes to infinity, the phase of the denominator would be 90,
Minus 180.
so the total phase will be minus 180. Well, this can also be shown graphically. If you have two poles like this, when omega goes to infinity, the vector becomes parallel to the j omega axis, this vector also becomes parallel to the j omega axis. So this angle is pi by 2 and this angle is pi by 2, and therefore phi j infinity shall be equal to minus pi. Agreed? Minus pi. So it starts from 0, remains negative and goes to minus pi. This is the confusion. If you had taken only the expression, you would have had difficulty interpreting whether it is minus pi or plus pi, because the tangent or any other trigonometric function is the same. And therefore the phase response, if I plot phi omega if I plot phi omega versus omega, the phase response would be like this. This is minus pi, this is 0, and pi by 2 is somewhere here. And it can be shown that the phase at omega equal to omega m is equal to pi by 2. I leave with a question mark, minus pi by 2. Phase at omega equal to omega m. Is that okay? But definitely I am leaving it with a question mark. Definitely the rate of change of phase is the highest at omega equal to omega m. That is, if you take the slope of this curve, the slope is highest at this point. The rate of change of slope is the highest at this point. Okay, that is as regards the phase response is concerned. Let us in the remaining period of time, let us take an example to illustrate all these calculations. The example that we take is a single tuned circuit in which the transfer function is of the form 34 divided by s plus 3 plus j5, s plus 3 minus j5. Actually it is given as, can you tell me what the polynomial form would be? S squared plus 6s.
It would be pi by 2 at omega is equal to omega.
No?
No,
So it will be.
Okay, you settle this controversy and let me know in the next class. That is why I left a question mark. Okay, here, come back here. This is how much? 9 plus 25. Is this 34? 25 plus, yes. It has to be 34, there is no other way, because the numerator is 34, omega n squared is 34. You can also find out from here what is omega n. Omega n is square root of 34, and you can find zeta. Zeta is, this factor must be 2 zeta omega n. So zeta would be equal to 6 divided by 2 omega n. So this is equal to 3 divided by square root of 34. Is it less than 1 by root 2 or greater than 1 by root 2? 3 divided by less than, because it is approximately 1 by square root of 11. No. Pardon me? It is approximately 1 by square root of whatever it is 1 less than 1 by root 2. So there shall be peaking. Will there be 2 peaks? We do not know yet. How do you know? How do you know so definitely whether there will be 2 peaks or not? The maximum value I have not found out yet. Okay. May I point out once again with a question mark sign, the maximum value in terms of zeta would be 2 zeta multiplied by 1 minus, well, I found this out, let me give you the result. Maximum value, no, I beg your pardon, is equal to 1 by square root of zeta squared 1 plus 2 zeta squared. So unless you substitute here, you would not know whether there are 2 cutoff frequencies or 1 cutoff frequency. It cannot be said by inspection. Okay. So there may be 2 cutoff frequencies, there may be 1. Let us see what is true for this particular situation. And the easiest thing to do for solving this example is to take help of the 2 circles. One is the peaking circle, this is the peaking circle, the green one, and the other one, in absence of any other name, can you give it a name? Half power circle we will call it, because this circle is used to define the half power points. So we will call this the half power circle. And you notice the locations of the poles, minus 3 plus j5, minus 3 minus j5. This is the peaking circle, and the peaking circle intersects the j omega axis at j4. Well, this can be found out very easily. Omega m squared would be equal to beta squared, which is 25, minus alpha squared, which is 9. So this is equal to 16, therefore omega m is equal to 4. Alright. It can also be found out by geometrical construction from here, any manner you like. Okay. Then what you do is you draw the peaking circle, let the peaking circle intersect the sigma axis at A. Naturally the coordinate of A, because this distance is 5, this is 3, and therefore this distance must be 2. Is that clear? This is 3, so OA must be equal to 2. That is the coordinate of A, the point A would be 2 0 to j0, okay, it is on the real axis, alright. Then with A as the center and AB as the radius. Now what is the distance AB? 5 root 2, this is 5, this is also 5, and this is the hypotenuse of a right angle triangle, and therefore this must be 5 root 2. With 5 root 2 as the radius, you draw the picking circle. This is the BC, and we had called this, no, we cannot call this anymore C, let us call this D. DBC is the half power circle. Draw the half power circle and you find geometrically that it intersects this at 6.78, J 6.78. Well, if you think you cannot read correctly this distance on a diagram, you can also find out analytically. After all you have to do is to find out this distance OC, and you notice that OC squared is the hypotenuse squared, that is AC squared minus OA squared. You know OA, do you know AC? AC, of course you know, this is the radius of the half power circle, and therefore this is 5 root 2, and therefore you can find out OC, alright, and the results are as follows. The result I have already told you, 6.78. Then to find out the maximum H of J4, well, there are various things you can find out in terms of zeta, or you can find out directly from the equation, that is it is 34 divided by magnitude of j omega minus, I am sorry, what is that, S minus 3 plus J5. So j omega minus 3 plus J5, j omega plus 3 plus J5, j omega minus, no, plus 3 minus J5, okay, magnitude of this, and substitute omega equal to 4, because that is the maximum, and the final result is 34 by 30. Well, 17 by 15 is the final result, less than, this is 1.133, less than root 2, and therefore there shall be only one half power frequency. And now if one asks you quickly, if one asks you what is the value at 6.78, what is the magnitude at 6.78? Okay, so it is simply 1.133 divided by root 2, okay, and the complete problem is solved. There is nothing that is unknown. Now through this example I also demonstrate that you can obtain an expression for omega c, the upper cutoff frequency, alright, you can obtain an expression for omega c in terms of alpha and beta or zeta and omega n, which I have not done in the theory, but you can do that, alright. That problem also I leave in express omega c2 as a function of alpha and beta. It is very simple, very simple. As I did here, all you have to do is to utilize this expression. You see, OC squared is AC squared is obviously beta times 2 beta squared, and OA squared is beta minus alpha whole squared, and therefore you can find out in terms of beta and alpha and substitute alpha as equal to omega n times zeta and beta as equal to omega n times square root of 1 minus zeta square to obtain the expression in terms of omega n and zeta. It may be helpful to have this expression also ready. Okay, we stop here today, we continue on the next Tuesday.